Right, notes for 9A from the Math 4 course. Again, some more, I guess you would call it cracked humor. Yeah, today we're going to be talking about the normal distribution curve, the mean, the standard deviation. We've really dealt with this before, so this is more or less a review. We're going to use the empirical rule to find out probabilities of events that are normally distributed. And we've also kind of dealt with that. I'm going to show you some more, which I haven't shown you yet. We've already talked about how 68% of the data should live between plus and minus 1 standard deviation of the mean. We're going to, there's some other numbers that we're going to learn. And finally, find the probabilities of events, and we're going to be using technology. I will say that what we're using with Desmos is a dozen times easier than what we had to do with the TI-84s. I was just having this conversation with one of my other teachers that, we get back in the building, everybody, next year. I'm seriously going to be considering moving away from the TI-84 in class and going to Desmos. Actually, Desmos does have downloadable apps for smartphones. I know they have it for Android. It would surprise me if they didn't have it for iPhones. All right. First of all, let's talk about the distributions. Since everybody is living on the left side of this one, the majority of the data lives over here, this is the weird stuff that sticks out here and throws off the average, throws off the mean. We are going to say that they are skewing right. And in terms of a normal bell curve like this, that is usually the positive side. So sometimes we will say that they are skewing positive. And likewise, everybody lives on the right side, which means we are skewing left. And that would be considered the negative end. And this one would be called a normal distribution. It has the nice bell-shaped curve. And bell-shaped curves happen in things like test scores and IQs and weights and heights and blood pressure and those kind of things. Things that you can measure like that. All right, symmetrical single-peaked bell-shaped curve. That's what a normal distribution is. It is defined by the mean and the standard deviation. Those are Greek letters. The Greek has both capital letters and lowercase letters. This is the lowercase mu, and this is the lowercase sigma. Now the area under the curve, we talk about the bell-shaped curve. The area that lives underneath it represents the probability of whichever part of the graph you're looking at. Wow, okay. Let's try that again. Probability. With the total area underneath the curve equal to 1 or 100%. And this area under the curve allows statisticians to make predictions on normally distributed events. And you'll see in a few minutes how that works. One piece that we do need to cover is the difference between discrete and continuous. When it comes to probability distributions, the discrete obviously is something that you can count on fingers and toes. But the continuous involves a smooth curve that if you grab a random point along that curve, chances are you're going to get an ugly decimal. It's not going to be a nice round number. Now, the empirical rule is the one that states that 68% of the data lives within one standard deviation, plus or minus, of the mean. This rule also states that 95% lives within 2 standard deviations and 99.7 lives within 3 standard deviations. Now, if we take those and we start breaking this thing apart into 8 little sections there, it gives us the ability to give a rough estimate on if we're collecting data, how many are going to show up in that given interval. And what we're going to look at is, of course, 68% live between the first, plus or minus 1 standard. That's 34 this way and 34 that way. And when you start looking at things like, 95% is within 2 standard and 99.7 is within 3 standard, you break it down, you get these percentages. These are worth knowing. This chart is worth making it really, really handy for anything to do with normal distributions, because this is how we're going to calculate what we're playing with. We're going to draw out the normal curve, the line down the middle, 3 to either side, and we're going to fill in values. For instance, if I had a problem where the mean was 50 and I had a standard deviation of 5 on either side, that means I'd start adding 5 for each 1s, 2s, 3s, or I'd start subtracting 5 going down this way. Well, that's not negative. Or 40, or 35. And so when we write the percents, the 0.15 and the 2.35 and so on, we can determine which part of the graph they're asking for. For instance, if they say, if these are test scores of some sort, what percentage of scores are going to fall between 50 and 60? And that would be the 34 here and the 13.5 here. You add them together, you get 47.5. That's your probability that the score would fall between 50 and 60, given that your mean was 50 and your standard deviation was 5. And so we'll be able to use these percentages to answer questions like that. And just, for all of these, we'll add up whichever sections are affected and add up the percentages, and that's going to be our percentage of, what's the chance of having the number fall between here and there. Now, Desmos, oh, bless its little heart. That is such a godsend for stuff like this, because trying to punch this into the calculator was a nightmare with the TI-84s. There were just all sorts of buttons you had to go through. And, students were forever forgetting, how do I find this button? How do I find that button? And it just turned out to be a nightmare. But Desmos makes it so much easier. Let's just go ahead and move on to the first problem, and I'll show you what I'm talking about. All right, so we've got a waiting time of 20 minutes on the average and a standard deviation of 4 minutes. Now this is, a lineup for tickets to a local concert on the phone. Well, or I guess maybe they're standing on the street corner or something. Anyway, so 20 minutes is the mean, 4 minutes is the deviation. So we're going to go back to where did it go? There's where it went. All right. As a matter of fact, I'm going to shrink that and move that over here. As a matter of fact, I can do split screen with this. And where did that go? That's going to go over here. All right, so now we can see both sides. So I'm going to go into normal. Oh, and I need to show you where normal distribution is first. We click in a box here, and then we go to functions, and we go to distributions. That's the third tab up there, and that's where normal dist is going to be there. And when I shrink this, normal dist has a set of parentheses. I'm going to do it 20, comma 4, close the parentheses. Now, when this happens, let's see now, 20 is where the top of the bell curve happens. And what they're telling me is that there is a 10% chance that some number out of this group, was it the number of waiting minutes they waited, there's a 10% chance you'll wait exactly 20 minutes. That's what that is telling you. But when we start talking about find the, and I'm going to go back here and I'm going to click that box, find the cumulative probability from negative infinity to positive infinity. That's a 100% chance of all of it. But look at what happened to the graph. The graph shaded underneath the curve. Now, something really cool happens here. When I want to know the percentage waited in line for more than 28 minutes. When I think about the number line, that would be like 28 to positive infinity. From 28 to positive infinity, I have an 0.2275 chance. Let's bring up this guy. So I write 0.02275. They did ask what percentage, so we would say maybe 2.3%. That would give them what they asked for. Now, something you'll begin to notice, and I talked about this with some of my classes, is that when I go to grab a number and ask myself, where do I chop it off? Where do I round it? I have a tendency to go for at least a certain number of digits that I want, which in this case, I would at least want 4. And the 5, if I bump that up to 0.228, I've rounded. But if I go all the way to 0.2275, that 0 afterwards means that if I chop it off there and leave off the 0.13, if I'm committing a rounding error, it's going to be very, very, very small. And so a lot of times you'll see me chase out, decimals until I get to something that is 5 or above, and then the guy behind it is below 5, and that's where I'm going to chop it off and use that. So let's at this point, I really did not need much past that first 2. I just needed enough to tell me 2.what%. Now let's look at the next problem. What percentage in line weighted less than 17? Well, less than 17 would be from negative infinity to 17. Less than 17, that's negative infinity, number line, up to positive 17, and that's where it stops. Now, I also want you to see what's happening to this graph. Notice how the shading stops at the 17. That's what we asked for. All right, so over here we're going to write 0.2266, and then that 2 afterwards says, all right, that's a good place to cut it off. And that's going to wind up being 22.7%. I at least would like 4 decimal places because that gives me a correct sense of where to round the 0.7, as it were. All right, 18 to 27. Well, all I have to do is go back to these blanks and plug in 18 and 27. This is so much easier than playing with the TI-84s. All I have to do once I have these numbers punched in is, change my terms, and it does all the heavy lifting. All right, 0.6514 would be 65.1%. Now, this last problem, we're going to need to look at a little bit more closely. 2,000 ticket buyers were in line. How many of them would expect to wait for less than 16 minutes? So it sounds like the first thing we need to do is figure out what is the percent of less than 16 minutes. Well, that guy is going to have to be a negative infinity. All you have to do is erase behind it and then click out of it, and it becomes negative infinity. And the same thing happens with a positive infinity. If I were to erase that and click out of it, he would go positive again. We said less than how many minutes? Less than 16 minutes. So that's going to be 16 is the max. And so 158655. Now I'm doing maybe an extra decimal or two, partly because I'm turning around and multiplying it by the 2,000 people. This is basically saying that 15%, 16% of these 2,000 ticket buyers are going to wait less than 16 minutes. Now I got to get a calculator and figure out what it is. Actually, this is the perfect time to say 0.15865 times 2,000. And that gives me 317.31. So I would say about 317 people can expect to wait less than 16 minutes. Now, these are the kind of problems that we're going to be dealing with in this section in 9A. This is 9A right here. Is the ability to use these standard deviations to create a percentage, and then in the real world, that percentage of the 2,000 ticket buyers or whatever your problem calls for. So let's move on to the next one. Here we have cars on the highway with a mean of 62 and a standard deviation of 5. So we're going to go up here and change those to 62, 5. And we want less than 55. That would be negative infinity all the way up to 55 miles an hour. And you're seeing a 0.0808 really. The thing is that after the 7, I'd have to go all the way to the 9 to chop it off with the rule I'm using. So it's kind of like, doggone it, I'm going to just round it there and say it is about 8.1%. Now we're talking about percentage of cars that average more than 70. That would be from 70 to positive infinity. And that's going to be 0.054799. Might as well say 0.0548. That's going to be 5.5%. Now we get to the interesting part. Police is stopping cars that are going more than 75. How many cars would they stop if there were 2,000 cars on the highway? So we need to look at what is 75 or up. And that is 0.00466 times the 2,000 cars. 0.00466 times 2,000. I got 9.32, so it's about 9 cars. About 9 cars that will be stopped out of the 2,000. All right, and then we'll go on to example 3, which is just a straight up how many problem. I will say those that are studying this to prepare for the Kahoot quiz with the next class. My Kahoot quiz will probably have 2 questions on what percentage and 2 questions on how many, because those are basically the 2 styles of questions that are getting asked in this section. So we have a mean of 50 and a standard deviation of 6. So we need to go back here. Mean of 50, standard deviation of 6. Oops. All right, now what we are looking for here is they will replace all batteries that last less than 38 hours. So we're talking less than 38. That would be from negative infinity up through 38, which gives us that kind of a decimal. Now, if we're talking about 50,000 batteries, I'm going to have a few decimal places. 0.2275, that 0 afterwards sounds like a good place to cut it off. And the thing is, I have 5 decimal places there. I have 5 decimal places there. So my rounding error is going to show up below this number. So I think I'm all right. Now, when I multiply these two, 0.02275 times 50,000, I get 1137.5. I'll call it 1138. So that's about how many batteries they'll wind up replacing out of 50,000. You know, sometimes companies have to anticipate this sort of thing, especially if they're going to give that kind of warranty on it. They're going to have to figure out how many are they really going to replace, because they have to figure the cost into everything else they do. But that is, I believe, the last of the notes. So that is your notes for 9A.